Thank you very much for the opportunity. I'd like here to speak about this our last paper that we had. I think it was 1 month ago that we put it out. Yes, been working there since I came to Bern last September. So let's see if I can. Yes, everything works. Good. So seeing the audience, I think I shouldn't spend too much time in introduction and motivation. So we all know why we are interested in these sort of systems, right? Conformal field theories in sector of large internal charges. They have an interesting phases that emerge, they're also found in quantum matter systems. So I think there's plenty of motivation there to study these sort of problems. Let me just add a couple of motivations that maybe they are more tightly related to what I'm going to discuss today. So we are going to see, I'll just spoil you, we're going to see that in these models that I will consider, we're going to have asymptotic series playing the role of large charge expansions. And they usually come with non-perturbative contribution to, in our case, scaling exponents. So it's not such a crazy idea to look for sort of universal prediction in forms of non-perturbative terms in this expansion, which in this case would be just e to the minus q, compared, for example, to the q to the 0 term of odd dimensional cases, or the log q that also Cuomo found, for example, in the equal 4. So that's one nice motivation. And more than that, we also would like to see in a controlled setting whether it's possible to extrapolate a large charge expansion to a small charge expansion, or to a regime of small charges or of order 1, which is also behind the motivation, behind the reasoning on why, for example, in the lattice computations, a large charge fit seems to explain also small values of charge. So as I say, yes, this is our work. We collaborated with Ioannis, Domenico, and Suzanne here on this thing, but I'm also going to be based a lot on their work with Alvarez Gauman, because I'm basically taking the same model. Okay, so the structure is basically follows a couple of macro arguments. So I would like to motivate and show you why and how the large charge expansion turns out to be an asymptotic series in this specific model that I'm going to talk about. As it's common lore that asymptotic series are actually a symptom of the presence of non-perturbative corrections of the quantities you want to compute. And Resurgence is basically a technical, not only, but is a technical tool for us to find what sort of non-perturbative correction are hidden in these non-perturbative contributions. More than that, this actually is a very general link. Every time I have an asymptotic series, I could see what are the non-perturbative corrections behind it. But on top of that, if your quantities you're interested, you want to compute, have an integral representation or a path integral representation, then in this language is sort of known that non-perturbative corrections, they're going to be related to semi-classical saddles, so instantons. And it's also been shown that in these cases, they will drive perturbation theory around these saddles to be asymptotic. So in this sense, this circle is going to be closed. And I'm going to try to basically touch on all of these sub sections in this example that I want to discuss. So first, let me start, yes, with convincing you that basically you should have asymptotic series in this large charge limit. To do that, I will of course focus on an example and then generalize by words. And the example is the O2N model in the equal 3, which is studied exactly by Domenico, Suzanne, and Alvarez Gaume. And why I want to focus on that? Because I want to basically exploit an extra control parameter, which is n. And basically, I can do my computations without committing to a particular EFT, which is, I know that is usually how this business is run, but in this case, I would like to have a microscopic realization of the system, which is just a O2N model with scalars in the fundamental. I will just consider, yeah, d equal 3 on the thermal circle times S2, just because I want to be on the cylinder in order to have my nice static operator correspondence. What are the charges? Actually, the charges that I want to consider is just a subgroup of the non-abelian group, which is the maximal torus subgroup, U1n, which is simply realized if one introduces auxiliary fields in this way. So if you want, we are still, the charge that we are going to use, the sector we are going to use are basically a generalization of an abelian case. Just the n is there because I need this extra control parameter. Then we know that all the observables that we want to compute are going to be found out of partition functions. So my grand canonical partition function is going to be just the trace over the Hilbert space with a given set of these charges Qi that I will specify. And conveniently, this can be written as an integral over the grand partition function over a subdomain of my charges here. This is basically just a character decomposition, but this is a U1n, so it's pretty straightforward for that. And these parameter theta are gonna also be present in my saddle point expansion in large N, which will be related to my chemical, what we use as chemical potential. So the actual parameters are chemical potentials and temperature. So let's see how this limit works. So I want to consider I will focus on the grand canonical partition function in the limit in which both Q and N are large, but the ratio is constant. And here for Q, for the rest of the talk, I will just generically call Q the sum over all these abelian charges. Then we know for as is a usual large N tool, one introduces a Haber-Stackeln of fields, which plays the role, which steals the dynamics of the phi squared operator. And basically, once that is introduced as a constraint, then it takes over the dynamics of these singlet operators. In this case, I will, however, single out two zero modes, which through a saddle point expansion are going to be basically the order parameters of the model, and they're going to be dependent in the end dependent from temperature and chemical potential. Also, as I want to focus on the Wilson-Fisher fixed point, I should actually study the IR limit of this model, because you know, the ultraviolet, this is a free theory of free bosons, but the infrared, it realizes this CFT that we are interested in. Just be careful there, because in this case is just going to be reduced by a limit of the quartic coupling to be infinite, and a conformal coupling which is going to be fixed. And in our normalization, it's just 1/4 on S2. Okay. And then, as we all know, the small temperature limit is gonna restore the conformal symmetry, and is gonna make us. It's gonna be possible from there just to extract the scaling dimension of the lowest primary with the set of charges that we choose of. So this is gonna be the main observable that I'm gonna consider in this delta. Okay, so maybe, I wanted to also talk a little bit about the technicalities of some technicalities of this saddle point expansion, because they turn out to be relevant at some point. So what you see here is basically the large N saddle point is going to be characterized by some saddle equations. And the variables there are going to be all the zero modes of the fields that I introduced, plus the theta parameter in my grand canonical partition function, which is just a chemical potential, if you want to think about it like that. And all the other fields have been integrated out, so it's actually a finite dimensional integral that you need to find the saddle for, and these are the saddle equations. A few things, so maybe it's better to specify that these trace logs are trace logs of differential operators, especially of nablas on the thermal circles, which also has now a twist. Actually, once you put your charge in your path integral, that will introduce a twist on the time in the time direction, as is evident here. And just to take that into account, it's not going to be extremely relevant in the beta equal to infinity limit, but still. And on top of that, these trace logs are actually well defined. If we use theta function regularization, we're just basically substituting them for the value, for the scheme independent value that they will have in dimensional regularization. And since we are in D equal 3, there are no actual divergences. So this theta function regularization gives the correct analytic continuation for this. So our equation, they just look in this way. I just didn't want to scare you because if there were some theta function there, you might be worried about it. But let's see what's going, how this, what are these subtle equations saying? So basically, the last one is just telling me that the chemical potential that are supported in this large N limit are all equal. So I'm basically choosing, it's a, basically, as you can see, is a fully abelian large charge limit, sort of. The other zero modes are the ones that are realizing the symmetry breaking, in which in this case we can see it directly through computation. And they're just proportional to the localized charge density on the SU2 submanifold. And finally, the last equation is just a sort of Legendre relation that relates the reduced value of the charge, so value for the charge for degrees of freedom, to a complicated function of chemical potential. Recall that this m square, which was the zero mode of the lambda field, is related to the chemical potential just via shift of the conformal coupling. So it's gonna appear, most of the time it's gonna appear m squared, and then I'm gonna say that this is a function of mu. Just recall that m squared and mu squared are related just by this simple constant shift in this case. Great. So once these are solved, where our critical exponent is just the action evaluated at this saddle, which in this case is also expressed in terms of a zeta function. So my whole problem basically is solved once I can invert the relation with in Q bar, so have chemical potential in terms of Q bar, and substitute in my delta. This is a delta hat because it's also normalized by 2n, so it's also a scaling dimension per degrees of freedom in large n. Okay. So these are the only two equations basically that defines my problem at this point. So let's see what we can do with that. Since the relation between Q hat and mu is highly nonlinear, there's no hope in inverting it unless we just work order by order. And if we do that, it turns out that we can actually look separately at two different regimes. There's no obstacle in doing that, which is small charge and large charge. So this small charge be careful about that because it's still large charge, but small compared to n, right? This is the ratio between the two. However, you see already that, so I can already tell you something about these two expansions. So the small charge, let's discuss 1 second the small charge one, because I will actually not come back to it again. It turns out that this is a convergent expansion. And this is not completely unexpected if you want, because we could think of this expansion as coming out of just a standard Feynman integral, Feynman diagrams expansion of our original O2N theory. And in large N, most of the time, the diagram proliferation gets suppressed, and you will end up with convergent functions, convergent series. So in that sense, is not so unexpected. Moreover, the leading order term actually shows that directly what is the operator that we are looking at. It's just phi q in this case. And since actually these two regimes are somehow connected by this set of equations, we also know that this is going to be the operator we look at also in the large charge. Basically, in large N, we should not have any level crossing or weird things happening. All right, what about the large charge expansion instead? Well, that one turns out to be asymptotic, okay? So there is going to be something interesting going on over there. So first thing that we should look at is what sort of asymptotic growth we are looking at. So in here, I'm plotting a ratio. This Fn is a typo. You should think is basically just an, so the coefficients of my large charge expansion, and is a specific ratio that I chose on purpose because I knew actually what was the result. If you see after a few, these are a few Shank transformations, so this ratio actually is not really converging that much fast, but once you use this technique of Shank transforming, you just sacrifice a couple of coefficients in the large order tail to get a better convergence. You can see that these ratios actually saturates at some value of order 1, which for the moment is not important, but is enough to argue that at large order, you're going to have a recurrence of this sort, which actually implies a factorial squared. So is faster than factorial growth. And I will anticipate that, I mean, this type of factorial growth actually should make us expect instanton or non-perturbative contribution in this series that goes like e to the minus square root of q. This is, if you want, is different from what happens usually in QFT, because over there you have normal factorial growth most of the time, and your exponential are going to be of order e to the minus 1 over g, where g is your loop coupling constant. In this case, instead, is going as square root. All right. Now, if we want to study directly the problem from the point of view of the scaling exponent, in this case, we should resort to numerical methods. Just because
I think Gabriele has a question.
Yeah. Oh, sorry. I think I cannot see. You know, the
Can you hear me?
raised hand.
Yeah, people should maybe speak up.
No, please tell me.
Yeah, no, sorry. Is this constant value related somehow to the convergence radius of the small charge series?
Is related to the radius of convergence of the Borel transform, which is I'm gonna talk about later.
Okay.
Actually, I mean, the whole analysis is gonna be carried through some derivative quantities, not exactly the delta. And the only problem with that is our relation between q hat and mu, which is actually makes everything more messier. However, I could actually study everything analytically if I, instead of this scaling exponent, I look into the ground potential and then computed everything from there. So yeah, but I'm gonna get to that. So yeah, as I was saying, I would like instead to look into that of just focusing on the ground potential, which is another theta function. And you can see that is exactly Legendre related to my original scaling dimension, and mu and q are the Legendre conjugate variable. So I'm just going to look at the factorial growth that comes out in omega, and then I can see numerically what happens in delta q, and I can also say what am I expecting to see also in my delta because of this. So here the problem actually is much simpler because it's just a theta function. So we know that this is a function that meets a Mellin transform relation with the heat rays on the sphere. Actually, on the heat rays on the sphere, is the conformal Laplacian. So most of the time now, I'm going to use theta functions. They're usually related to the conformal version of that Laplacian, which is still only a number away from just the Laplacian. So it is evident that if from this expression I want to construct a large mu expansion, which is actually my large Q expansion because this relation is monotonic, I should look into the small t expansion of my heat trace. So my large charge behavior is just going to be related to the small distance behavior of my heat trace on the sphere, on the manifold that I chose. In here, I mean, this is a sort of a known problem. I mean, this expansion is the Siri-DeWitt expansion. For this case in the sphere, you know that this trace has asymptotic expansion, which grows factorially. So How you see it, you have Bernoulli number that grows like a double factorial, but then you divide out by an extra n factorial. What does it mean for the ground potential? Well, if you just plug this expansion inside this Mellin transform and wildly permute sum and integration, you're gonna see that order by order, this Mellin integral is gonna just enhance you with an extra n factorial. So your omega, your ground potential is gonna carry the double factorial growth that we just observed before, just numerically. So you see that in this case, however, we can do everything basically analytically. Okay, so now I would like to talk about the sort of non-perturbative correction that should come out in the ground potential or in the heat kernel slash ground potential because of this factorial growth, right? And I will start just by introducing some typical tools that are used in resurgent analysis. I will just flash the few things that I'm going to be needed. The subject is much wider than this. So what are we dealing with is a prototypical perturbative problem, right? You have an observable, which is defined, if you want, as a path integral. That's the thing that I always have in mind. And I want to associate to it an object, a series, which in general is going to be formal in a given limit. In this case, I'm looking at z going to 0, for example, where z is a coupling constant, if you want. Why do I say that these objects should be considered only as formal object? Well, because in principle, I want to consider larger than factorial growth. So this beta here is exactly the factorial growth order. So what do we do with this series? So you know that this series cannot be summed in the usual sense that we do with convergent series, because they give a nonsense after a while. The terms, they all start to diverge, and you don't get the usual, the more term I add, the more accuracy I have. So the usual machinery to deal with this is to define a transformation of this object, which actually improves the convergent structure. So from my, this transform is called Borel's transform, and is just obtained as a series in which I divide out the factorial growth, basically. So if I had my an growing like a bn factorial, then dividing out by a gamma with an offset, these are all parameters that you have to tune in order to have this thing convergent, then this is going to be a convergent series. And this Borel transform is going to be a function defined in a given radius of convergence of his complex plane, which is called Borel plane. And it's going to have singularities. It's going to be possible most of the time. I mean, you always assume that it's going to be possible to go outside its radius of convergence, so you can analytically continue basically everywhere. And usually in physics, this is always a good assumption. And okay, so that out of that, what can we do is to actually build a function, a full function. It's called the Borel summation of our original series, which is actually just inverse Laplace integral of our Borel transform. So in which sense this is a function? Well, this is a full function in the sense that if I plug any value of z, specify a theta angle in which this integral runs to, then this is going to spit up a number, thing that your original series was not really able to do. Now, this is going to happen only if some conditions are met, basically some regularities of your Borel transform. Moreover, notice that actually this function that we constructed, so all of these factors are not, of course, random. Once you decided what is your definition of Borel transform, so in this case for me it's just dividing by 1 over gamma beta m plus b, all these factors, they all comes automatically. And why? Because you want to have this function to have the same asymptotics in a small z of your original series. So basically, if you now plug back your Borel sum in here, and again, exchange wildly integral and summation, then order by order, this integral is such that it's going to cancel out this gamma function, and you're going to be back to your original series here. Okay. But just to stress, this is not, in general, this is not a formal object. This is a thing you can put in your Mathematica and compute. Let's discuss what are the properties, because of course, if it would be that easy, it would have been already over. So let's discuss the case in which everything goes fine. So the case in which everything goes fine is the case in which this you're integrating along rays. So you choose this parameter theta to integrate along direction in which your Borel transform doesn't have any singularities, right? I'll also assume that at infinity there's always a nice convergence. This exponential is never overtaken by anything else. So what happens for a general theta is that this whole integral is going to define analytic function in a half plane. So in a half complex plane, if I actually choose beta to be 1, so actually this plot, if you want, refers to beta equal to be 1. If it's different factorial growth, then you're going to have wedges, but the situation is more or less similar. Now, if I choose two different angles, right, two different angles of integration in which there is no singularities of the Borel transform in between in the Borel plane, then in Z, this function actually can be these two functions integrating around two different angles are actually coincident. So they actually provide an analytic continuation of itself. So if everything is satisfied in this way, then you're just extending the domain of analyticity of the function you just defined. Now, of course, this cannot go forever. At some point, I'm going to have a direction of in which this is going to be singular. So I cannot have a function which is analytic everywhere. And why this is so? Well, it's just because we started with a factorial growth and we divided out. So we know that this Borel transform has a finite radius of convergence. So at some point, it's going to have a singularity. And this also implies, in fact, that this function that we ended up with, corresponding to our asymptotic series, is not going to be analytic anywhere. It cannot be. Okay. So what happens when we actually hit these singularities? Well, suppose that, for example, we have some theta c, which is a singularity in the Borel plane now, not in the Z plane. And in this direction, my Borel transform has, for example, a pole and a branch cut, right? So it's not going to be true now that in the Z plane, if I integrate slightly above this direction and slightly below, these are going to give me two coincident functions, one analytic continuation of the other. They're going to be different, actually. But their difference can be actually written right away, right? Because it's just an integral over the singularities of my Borel transform. So in this simple case, for example, in which I have just a pole, let's just look at the pole contribution. The difference between the two summation is going to pick up the residue of the Borel transform, and all the factors that I have in here, they will actually be computed at this value of the singularity. Which in this case, I just call it omega. So what is peculiar of this form is that this is a non-perturbative contribution. This starts with e to the minus omega constant divided by z. So this cannot be expanded as a power series. So what we are saying here is that our way to deal with that asymptotic series, we have one, we can produce functions out of it. However, the function that we produce out of it is actually multi-valued. And the difference between the various branches is non-perturbative, okay, is only non-perturbative. Okay, how do we deal with this case then? We would like to have like a unique, a sort of a unique answer, if possible, right? For our end result. We want to have a unique summation of our asymptotic series. So one way that the way that actually this is solved is just simply by enlarging your ansatz. So at the very beginning, I saw, okay, my ansatz for the asymptotics at small coupling is just going to be a power series. So what we do instead, if we enlarge it, if we start, instead of considering only asymptotic series, to put what are called trans series. Trans series have a structure which is basically a structure of a saddle point approximation of an integral, if you want. You already seen it there. You have a perturbative series, phi naught now, plus various non-perturbative contribution, which looks like this AK, for example, could be like instant on actions, and then extra parameters characterizing your non-perturbative part. So in this sense, this is not anymore Poincaré asymptotics, because now these terms that I have like 0 power series. So I'm enlarging it to assume that also you can have also these contributions. In here we have introduced some parameters, extra parameters that you don't have before. Before you had only a coupling constant Z. Now you also end up with these trans-series parameter, which are, if you want, they just count the instanton factors. Like there's one for each of these non-perturbative exponentials, and in general, complex numbers. So, okay, now the same thing could be carried on, right? So in principle, all of these series appearing here in my trans series are asymptotics, so they need to be taken care of. So let me try again to just go through a cycle of Borel summation, of Borel transforming, and Borel summation. Okay. Now, recall, just mentioned that Borel summation and transformation, they just act on the asymptotic series. So they just, all the other numbers and non-perturbative parts, they just go through them, right? And what is nice is that, as before, right, the summation of a trans series is going to be an analytic continuation of itself in various directions that you integrate of if you don't have any singularities for the Borel transform, for each Borel transform of all the asymptotic series that you get here. But now you have the thing that if instead you cross a singularity, you don't generate something that was out of your initial ansatz, but because you chose all of these non-perturbative terms to match the discontinuity that you were creating from the asymptotic series of the perturbative part. So if I go back again and again go through a singularity in the Borel plane, then the summation of the phi naught is going to generate a term which has the same form of the next non-perturbative correction, and that will just boils down to a shift of the trans-series parameter by a given number, which are called the Stokes constant. Okay, so these Borel summation of trans-series have this enhanced, if you want, analytic continuations, and actually these continuities in Stokes parameter are actually incorporating what is called what's known as Stokes phenomena, which we don't really need to go into there. Okay, so now we would like to know now under which condition we can say that our original observable can be said to be equal to our sum the trans series. Here I need a summation, actually, I forgot it. This should be equal to the summation of the trans series in the Borel summation of this trans series, because that reconstruct the functions, right? And we would like to say, okay, this function is actually reconstruct completely our initial quantity, not just the perturbative part, which is asymptotic. So under which condition this can happen? So first, you can already see that, for example, this Borel sum has a lot of new parameters that I don't have in my original definition, right? I only have Z, my coupling constant. Well, it turns out that for all this framework to be consistent, you're going to have what are so-called large order relations. So basically, the large order behavior of the perturbative part is actually contains a lot of information on most of the non-perturbative information in the other sectors. It actually contains all the instant-on actions, all the various parameters for non-integer powers, and even the entire series in the fluctuations. Okay, we already see. I mean, we sort of hinted at this large order behavior, right? When I said that the singularity of the Borel transform is going to give to me the form of this non-perturbative contribution. Well, the singularity of the Borel transform, you're going to see it only if you go to high order, right? Because the singularity is actually going to be found only once you introduce infinite orders. If you truncate your Borel transform to a given order, well, that's a polynomial. It doesn't have singularities. So you need all of them in order to resolve these things. However, you are left with an ambiguity in these trans-series parameters, which is not unexpected in the sense that in the Poincaré sense, you know that all these functions are asymptotic to the same thing, because all of these non-perturbative parts are actually asymptotic to zero. So no matter what are your parameters, if you really restrict yourself to Poincaré asymptotics, they won't matter. You're going to always have the same series. So we sort of have to, if you want, we sort of have to live with these ambiguities unless you find a way to fix them, right? So if you want, like what Resurgent can do for you is to find from the perturbative series all the information on the structure of your non-perturbative parts, but then you're going to left with this small non-perturbative ambiguity that you have to fix somehow in some way, right? So what are the popular, most used way to do that? So, for example, if you know that your trans-series is going to solve a differential equation, then you know that there's going to be initial condition that you have to impose, and this will fix, for example, part or some of these sigma k. If you don't know anything, and that's usually the case, for example, in QFT, sort of, you could impose like reasonable condition, like, for example, that my observable is going to be real every time that my Kaplan constant is real. So that's a condition that might give you some hope. Or otherwise, you can just, if you have a decent non-perturbative definition that you can compute, well, an immediate comparison gives you all the correct thing that you want. And whenever this can be done, then you can really write an equal sign. So you can say that you have summed your perturbative series. You know in the value that you want to look at for your couplings, it's going to be real. Most of the time, it's going to be real. You know what are the non-perturbative contributions that are there. You know what is their magnitude. And in these cases, what you say that you can actually say, okay, I recovered the entire thing. I'm able to extrapolate my asymptotic series up to any value, right? And this, for example, is called it's called semi-classical decoding by some authors like Marinos and al. And it's called like that because mainly in this form, right, the thing that you're going to obtain is actually a semi-classical expansion. What it seems to you like a semi-classical expansion. So to just make this a little bit more clear, maybe I want to go through a small example, which actually is relevant for the heat kernel case of the large charge expansion. So let me consider, like, this is a classical example in which, for example, you can do everything. And let's say that you want to find the solution for this equation. Is just an first order ODE, which is non-homogeneous, right? You can see that, for example, z equal to infinity is a singular point, but you can find easily actually a perturbative solution around the x equal to infinity. You just plug an ansatz as a series, and you see that this differential equation is going to be a recurrence relation. This recurrence relation can be solved and gives you like exactly a closed form for your coefficients, which is going to be factorially growing. Okay, so you have found a solution for your equation, but is an asymptotic series. So what do? Well, we define Borel transformation and Borel summation for this series. I chose it just to cancel out exactly, as you can note, to cancel out exactly my gamma enhancement, so that my Borel transform is very simple. It only has one singularity at 1 in the Borel plane, and the corresponding Borel sum is going to jump exactly on the as I go from 0 plus to 0 minus, right? So these are the two different summations that I should consider. All right, so the difference between these two summations is actually very simple, is just the residue of my Borel transform at 1, which is just a number, times all the measure in here at 1, which is just an exponential of this form. So from here, I would say, okay, then let's try to see what happens if, as my solution, I use instead of a just normal series, a trans series, in which I turn on this extra non-perturbative contribution. So you go through the same thing, and you find that your summation, either plus or minus, is going to be of this form, where your parameter has to be chosen somehow, and is different depending on, I mean, is in general different from if you integrate above or below your axis, the Borel axis. So this solution is a well-defined solution, is ambiguous if you want, because you don't know if you want to choose up, above, or below, but it solves the original differential equation. If you put it in here, in your original equation, it's gonna give you, is gonna be a solution. And you also notice that the non-perturbative part that you just introduced is itself a solution of your differential equation, but the version that has that is homogeneous. So if you take away the 1, well, this non-perturbative part is going to be a solution of that equation. Okay, now in this case, you know why you end up with an unknown variable, right? I didn't specify for you an initial condition for this equation, so I should not be allowed to find a unique solution. So it's okay in this case. But let's suppose, for example, that we don't know that, right? Suppose that we are given this series and we just have we want a way to sum it. Then one way, for example, to fix some of these ambiguities is to ask for a reasonable condition. For example, for this function to be real when his argument is real. Well, you're going to see that this is going to fix only the imaginary part, for example, of your sigma plus minus, just in order to cancel out the residue part that comes from the Borel integral, right? However, the real part is unfixed, and in principle, you don't know what to put there. So this is also used in, for example, is also known as median summation, and is known to be enough in the case in which you have thimble decompositions in a series that comes from exponential integrals. So most of the times, also in field theory, for example, this would be one of the few and only conditions that you can impose. Here, of course, you also know that this is a ODE, so you can just impose, for example, this function to be 0 at 0, and that fixes also your real part to be 0. So this particular solution, the one that vanishes at the origin, is also known as Dawson function. And we have basically completely reconstructed it from the asymptotic series just in this way. We just we can take, for example, the upper Borel sum and then choose the correct value of the non-perturbative contribution. And then we have an unambiguous result, which is also related to the R5 function, but okay. And in a couple of slides, I'll tell you why I show you this thing. Because now I would like to look at what happens.
Oh, sorry, I have a question.
Yes, sorry. Yes.
No, it's a stupid question. But what happens if you have a branch cut? I mean, it's not relevant here, but I was interested in it.
Yeah, no, it's actually, I mean, it's a very interesting case. If you have a branch cut, your discontinuities is not just going to be an exponential, but it's going to be a full integral over this branch cut. Which you can use a spectral decomposition to just rewrite it in and solve it and basically integrate order by order, and your end result is just basically that you're going to have an entire fluctuation series here. Okay, so it's not going to be e to the minus z squared, but it's going to be these times a series in z.
I see.
Okay.
Do we know an example in logical expansion where this happens?
No, because now we only find simple poles.
Yeah, true.
Okay. These happen.
What about
something like this
some expansions?
Studied by Zohar, Alba,
Right.
and others?
Sorry, you're very low in volume. I don't know if it's just me.
Epsilon expansion. So Gabriel, what about epsilon expansion? Was not didn't it have branch cut or something?
Well, I mean, there we didn't extract analytically, but I thought in the case studied by Zohar, Alba, and there they have a exponential with a full series associated, right? So your branch cut.
I see.
Okay.
Very good,
Okay,
great.
Okay, I was not right. So here in large N, we're probably just suppressing all of these things. But yeah, I mean, there is no reason why you should not find it in principle. Okay.
I see. Thanks, both.
Yeah.
Yeah, but in fact, if you look at the last paper of Simeon by himself, he starts computing all these terms, right? I mean, he shows that they have to obey a certain equation, precisely like here, and then he computes them one after the other perturbatively. So presumably that is going to be a branch cut, if you can do an analysis like this.
Yeah, recall also that it also depends on the way you define your Borel transform. I mean, if you're smart, sometimes you can turn a branch cut into poles, right? But depends. If you have both, for example, no. So I mean, you can have pure branch cut or not, because these things are somehow also related on the way you want to parameterize your Borel plane. So there can be some variance, but yes, there are in principle. So if you want this is a one loop exact saddle point expansion. So let's proceed and show you what happens, for example, for the heat kernel. So I basically do the same for the heat kernel and see that Borel transform has a lot of simple poles on the real axis, right? At each integer value of pi. So again, I have an ambiguities in where do I want to make my Borel summation, and my discontinuities is going to look like this. So a lot of exponentials, one for each non-zero integer, with instant on action, if you want, pi squared, k squared. And in this direction, I can have my Borel sum, which is going to be the first part is just the Borel integral of the perturbative part, and then I have all of these terms that I should include. Okay. Now you might say, okay, these of course I'm going to feed it into my ground potential, which is going to be fed also in my scaling exponent, and all these sigma k ambiguities, they're going to always be there, right? You cannot get rid of that. I mean, the procedure is linear from there. So we have to have a way to fix it already from here if you want to. It looks like there are infinitely many. There are one for each non-zero integer. But I mean, in the end, this is a heat trace. So we know there are so many things that we can impose that are actually should be imposed on this quantity in order to fix it, because it's positive definite, is a solution of a differential equation, which is a PDE, but okay. So we know that there has to be a way to fix all of them. Well, the simplest way that I can tell you is just by using a Hilbert trace formula for this sum. So if you want, it's basically a Poisson summation, but for the eigenvalues of the sphere. And if you apply this, you basically find a representation of this heat trace in terms of a sum of Dawson functions. Okay, so here you have a lot of Dawson functions, each with a different argument in k, and we already know how to fix that, right? So we can that is fixed by simply requiring positivity, and is automatically 0 at the origin. So all of these ambiguities can be fixed, And it can also be used then to be fed to obtain a ground potential, which is in closed form and unambiguous. So this looks like a Borel summation, but it's sort of a Borel summation, just that instead of exponential, you have a Bessel 2. This comes out on just as a Melling transform of our Borel summation of the heat trace. Finally, of course, the relation between M or mu and Q hat is nonlinear, so we cannot have a closed form result for the critical exponent. But we can see immediately what is the leading non-perturbative contribution, which should come out, which is exactly e to the minus square root of q with an action which is a 2 pi k. Okay, and this is the leading one. Then you can have also other ones, and in this case you can also have series depending on how exactly they fit into each other. We really didn't go into that because you need numerics to see this. What instead now I would like to show you is, okay, I mean, you might say, okay, I mean, you went through this procedure to get out this shape of non-perturbative correction that you should have. Do you have a physical interpretation or some sort of more immediate way to get to the same result? Well, yes, because at least for the ground potential, there is a way to recast it into a path integral. And this path integral is going to have a semi-classical expansion in which you're going to have all the non-perturbative correction coming from those saddles. And the fluctuation around those saddles are going to give you back your asymptotic series you started with. So I don't know how much time. Oh, no, I should stay in the time. Right. So let me tell you just a little bit of how this works. I mean, it's a trick that has been used in a lot actually of problems in QFT. It goes by the name of worldline formalism. It's basically, the basic idea is just to rewrite a one loop determinant in quantum field theory just via quantum mechanical path integrals. And it goes it uses a relation which is very similar to the Melling transform that we used before. So on one hand, I have a log of that, and on the other hand, I have an integral over the trace of the exponential of that operator. So in this small example that I flashed, for example, is what people were doing when they're studying Schwinger effect. So they were looking for, wanted to compute effective action for electric fields once you integrate out electrons, for example. And you usually end up with, for example, a log that of this sort, where you have a U1 covariant derivative. Well, it turns out that once you exponentiate that in Schwinger proper time, everything can be rewritten as a path integral for a quantum mechanical particle which is moving on a field background. So because here I end up with a trace, this quantum mechanical particle is moving in loops. So this is just a set of loops over RD. And this is just a minimally coupled relativistic particle on the under the effect of an electromagnetic field of mass m squared. Right. So we can write something of the sort also for our ground potential, because also that one is a one loop determinant. So we end up with a slightly different action, which is basically the action of a particle of mass mu squared on a that circles loops on a manifold, which is the cylinder, okay, in the large B limit. But as long as you stay at finite B, of course, it's going to be a thermal circle with a twist given by the mass of the particle, which is slightly unusual, but it gets washed away as soon as you take the beta equal to infinity limit. And the particle is moving on this curved manifold and is conformally coupled, okay? So you have a conformal coupling there. Of course, you can integrate out the S1, the thermal circle part, which is just a dimensional reduction, and write everything in terms of a path integral just on for loops on the sphere. So at this point, you will recognize that you have basically obtained a path integral representation of your heat trace. And this path integral representation is going to have a saddle point approximation, which we are now going to briefly look into that and show you that you exactly get the result we had before. So the general structure, this is what we expect as a general structure, right? You're going to have a perturbative part for this integral, which is going to reproduce the Selite with perturbative expansion. Actually, people computed these up to, I don't know, 6, 7 orders also for the sphere using this worldline integral, so you can do it. On the other hand, you can have instantons, right? Or like non-trivial loops on the sphere that you can write, and each of them are going to come with a fluctuation, right? With a series of fluctuation around it. So what sort of instanton we can have? Well, these are just, since the Lagrangian is just the line element on the sphere, these can only be geodesics, and non-trivial geodesics that we can write on the sphere are just great circles that wind around. So let me just introduce a winding number W, and these curved gammas are just going to be winding geodesics around my sphere. If I, as usual, instanton calculus, I just expand around these solutions. I found the spectra of fluctuations, and this is just going to be given by this formula here. Basically, you have n fluctuations. Some of them, as you can see, are going to be positive, negative modes. Some are going to be positive modes, and there's going to be a zero mode. So your computation is just going to be related to computing the functional determinant, taking into account correctly all these modes. So all the modes, of course, that going to have a mode number larger than twice the winding, they're going to be massive. So these are going to be all nice, and they're going to be deformation of a great circle on the sphere. There's going to be one zero mode, which is the one that has mode number equal to twice the winding number, and just implements the fact that you have a overall rotational symmetry. This is an effortless deformation of your path. And finally, you're going to have a bunch of negative modes. And these negative modes are there because you know that these paths are not topologically stable. You know that the first homotopy group of the sphere is trivial, so all the loops are contractible. So I am expanding around instantons if you want, but those are not stable. And the effect of these negative modes is basically to introduce a Morse index, which comes just simply from the way you analytically continue the Gaussian integral for these modes. This is going to spit out exactly a factor of I for each of these negative modes, which are all independent, because each of mode you can always choose if you want to continue his integral in a way or in the other. But once you compose all of them, of course, if you have an odd number of I factor, in the end, you're going to have a plus minus I. So let me put everything together. And what we find at leading order, right, if we just compute the functional determinant around these geodesics, is going to be a leading order result. It's going to be, okay, the first term in the Selite with expansion is simple. All the Morse indexes of the negative modes around each winding geodesics is going to spit up a factor of plus minus I. Now, for each winding, this plus minus I can be different, right? You don't have to choose the same for each of them. But now, for the moment, let me take plus I or minus I for all of them. Other than that, of course, you're going to find that the action of this instanton is exactly the length divided. There is a factor of 4 going out. So it's just going to be the length of your geodesic, and this is going to be exactly the structure that you found before in Resurgent, right? Just using a large order analysis. A few comments. So the instanton fluctuation from this formula, right? We didn't go through beyond the leading order, but there seems to be a strong suggestion from the large order result that actually these instance fluctuations are all vanishing. And these actually, if you actually do properly your saddle point expansion, you're going to find a one loop exact result. This is perfectly reasonable. We just didn't check that because while this computation of this functional determinant does not care about any type of regularization, once you want to consider fluctuation around them, you're going to have to proper treat this as a 1D sigma model. So you're going to have an interaction, you're going to do Feynman diagrams, you're going to have to introduce some some regularization. And so we didn't want to commit, but of course, these I mean, is expected to be 0 to all order and reproduce exactly the formula that we got here. Okay, so I think I can reach the conclusion now. So what we did, we did focus, even though indirectly, of course, especially in this last section, I just looked at the heat trace. But as I told you, everything goes through all the steps to give me a well-defined ground potential, well-defined scaling dimension. And what we saw is that, okay, the regime for small charges is given by convergence series. The one for large charges is asymptotic with a factorial growth going to as a double factorial. We do not expect, of course, the convergence series behavior at small charge to be stable under n correction. So basically, this I think is a feature of large n, while is the asymptotic nature of the large charge part, I would be surprised if instead gets smoothed out by the 1/n correction. So there might be a way actually to prove that you have to have an asymptotic series independently on the fact that you're taking a large n limit. You might not be able to see the degree of the factorial growth, but I think this is a sort of a solid result. So we also saw that that actually this asymptotic series is not Borel summable, but you can find a complete non-perturbative unambiguous function without imposing anything new. So you have a smooth interpolation between the two regimes, and most importantly, maybe to appreciate this, is that you don't need any further information on fixing all the non-perturbative corrections. So your problem, if you want, the problem of getting this large charge expansion is well defined. You don't need extra non-perturbative information on that. I would say also this one might survive 1/n correction. This should survive 1/n corrections, of course. And lastly, we saw that there are, what is the origin of this factorial growth, which is just given by these so-called worldline instantons, which has also been used to study the Schwinger effect. And in this case, that just comes out to be unstable saddles of a quantum mechanics path integral. And this is also a nice example, because usually people also tend to say that, you know, your non-perturbative correction are given by instantons, and instantons are basically classified by stability of homotopy groups, right? And that means that, okay, you have instantons that are only topological stable or not. Well, what is a feature of large order growth, that factorial growth can be driven also by unstable saddles. And this is a case in which this actually happens. And from that, yes, I think I can finish here if there are questions.
So thank you very much for your talk. Are there any questions for Nicola? You can just speak up or raise your hand, or
yeah. So I'm just a bit ignorant on the topic. So perhaps what would I gain anything if I do Borel? I mean, if I start from the small Q expansion, can I get any hint about the large Q behavior by doing some kind of trick? So by playing some kind of opposite game.
You want to go in the other direction?
Yes, it's like that's what, for instance, what typically say in the epsilon expansion, we have a 5-loop result at small charge, say, something from people. So can they, to what order they can compare with Monte Carlo at large charge after Borel summation or something? Like, that's kind of a question someone might ask. Do you know, do you have any comment in that direction?
So, well, I didn't comment in the end about this, but I mean, you can see that, for example, the correction that you get, I mean, I would more say, okay, I start from large charge and try to compare to the small charge regime. You can see that these corrections are actually so numerically small in the case that we are looking at. So these full formulas that you get here for your I have somewhere, well, yeah, for your grand potential or your your scaling dimension, they match pretty closely your small charge expansion, even if you use, I mean, we were using a lot of terms because we have all of them, right? So we could have like the accuracy that we wanted. We didn't really did like this is actually something that we might be interested in the future to do a proper numerical study to see what is the actual amount of terms that one would need. I don't know if 5 loops would be enough to match with a large charge expansion, even if you start introducing these non-perturbative corrections.
Well, it might be that it is, no? I mean, the number that we give in the paper actually is done with five loops, because there was no point in adding more than those. And like this, we already had like 12 digits accuracy kind of thing.
So, 5 loop for the small
or charge. It was 5
small charge. Yeah.
Small charge was giving. I mean that at some point there the convergence was so fast that after 5-6 terms it was already good at 12 digits. I mean, since we have everything here, we know what happens, right?
Yeah.
And there it turns out 5-6, more or less, were already enough, and we were reproducing the same thing from the other side, with the exponential corrections.
Yeah, the only trick is that maybe, you know, in this case we have all the coefficients of the large charge one, all the Wilson coefficients are known because they are the leading end, right? So now your problem becomes to know those.
Right. Yeah, I mean, here it was just particularly easy because we knew everything on both sides. So we could just play with it. But at least it should give an order of magnitude of when things work, you see? So
yeah.
It looks, at least a large n for this model, it looked like 5-6 terms were okay to give you something stable enough.
So you mean 5-6 terms on the large charge?
The small charge.
Small.
So to compare with the resummation of the large.
That's correct.
Yeah.
The resummation, on the other hand, that was painful because there you really have to solve all these integrals. And then, so like the kind of thing, we have a number there in the paper that agrees 10 digits, something like that, but it took Mathematica 24 hours to solve an integral. Literally 24 hours. And each new term in the integral was doubling the time or something. So
I mean, over there could be room for improvement there, right? I mean, that I want, there could be. The only problem is like, knowing the Wilson coefficients of the large charge one, if you want.
Sorry, I must have missed the talk very badly then. I mean, I thought you were trying to determine from the perturbative part of the large Q expansion, you determine the worldline instanton corrections.
Yeah.
On how does it? And then you talked about small Q expansion. How can they be related? I mean.
Well, it's just a matter of, once I'm able to resum the large charge expansion, including all these non-perturbative contribution, I could extrapolate up to small,
I see.
Small charge.
Thank you. I see.
And then I can start comparing with the small charge.
I think I have another question. So can you do the same thing for, I guess you can do the same thing for CPN at large charge, right?
I guess. Well, in a large n limit for CPN.
Right.
So here, for example, large n played a role for like this for having this closed form relation. So if it's just different model, different base group of the sort, I mean, you can probably play the same game.
Yeah. So can we turn the story on probe like n equals to 4 or 5, where you don't know if fixed point exists or not, and then say something about the existence of it?
And say some, yeah, it's it's a good question. So what needs to go wrong in order to conclude that you're actually you're not having, I mean, you want to say that something like okay, the CFT is actually not allowed by some unitarity bound of sort, right?
Right, or the complex dimension or whatever.
Yeah. I don't know. I don't know, to be honest, if
but you don't really have control over what happens in 1 over n here, right?
No.
Yeah.
I mean, for the vector models, you know that you expect that stuff that happens at large n keeps happening, and for the CPN you expect not. But at least this kind of work is all done in the large n regime, which is really separated from what happens for n equals 4 in CPN.
Right.
So,
right.
In the for vector models is different because you expect things are related. I think.
I see.
Interpretation with the borderline instanton might survive in other model in large n because it's just related to the base manifold. So that could very well be. But yeah, beyond that, I wouldn't.
I see. I see. Okay. I see.